Good morning, everybody. Welcome back to term 2. Hopefully this isn't as awkward for you as it is for me, but we're all starting to learn how to do all these things together. Hopefully we can still get something out of it. All right, so first thing I want to do today is I want to go over hyperbolas, which we started at the end of last term before the early finish, and then I want to move into truncuses. Alright, so as you can see, I've got my CAS calculator set up on the right hand side of the screen, and hopefully that will be able to be used at some point. But right now I want to do some little bit of notes on the board here. So, remember, a hyperbola is of the form y equals a over x minus h plus k. And what that does is it creates a graph that looks something like this. Alright. Alright, if you can't see the video, again, it is going up. Video. Alright, so we have our y equals a over x minus h plus k. And what that does is it creates a graph that looks something similar to this. But what it also does is create hyperbola. So, get my nice little ruler out here. Like that. This is chapter 4. 4A and 4B today. Alright, so I've got a very, very, very rough set of axes here. Let's get rid of those. Sorry, I'm still learning how to use this tablet myself. Alright, so a over x minus h plus k. The graph will look something, oh, wow, that I really cannot draw with this thing. Now in this case, h and k are both 0. So this is the equation 1 on x. And what it has created is it has created asymptotes. All right, and the asymptotes are located along the axes at x equals 0 and y equals 0. All right, asymptotes again are lines that imaginary lines that the graph will never ever touch. All right, and when we change h and we change k, we are moving the asymptotes left and right in the case of h and up and down in the case of k. What A does is it stretches and moves away our graph and moves it so if A is a very large number, the graph will move further and further away the larger it is. All right, so let's go over to the CAS and we'll see that in practice. So on the CAS under graph and table, what we want to do is we want to create equations with some variables. So we're going to go a over x minus h plus k. And then we want to create the graph with variables, so we're going to press this button here. I knew that was going to happen. So we're going to press that button there and create some sliders. All right, now we need to set our window properly. We want x min, we'll just go minus 10, x max 10. Y min minus 10, x max 10 as well. Now we have our graph looks like that. Obviously if A is equal to 0, we don't have a graph because everything's just divided by 0. Right now we have our hyperbola. And as you can see, there is that asymptote running up and down and left and right. Now, if I move the h value, it will go, if h increases, remember I've put it as minus h. So if h itself is positive, we're moving it to the right. If h goes into the negative, we are moving it to the left. If you cannot see the calculator properly, you need to stretch your screen. Go full screen, please. I'll move it into the middle for you. So, K and H, moving it up and down. So sometimes what will happen is the graph will have a center, and that center value is determined by H and K. It is simply the coordinates that both of the asymptotes intersect. Now, as I increase A, as you can see, what it does is makes it stretch further and further away. But if I also go into the negatives, it flips the graph upside down, same as it would for any other graph with a negative A value. Now, the one thing this graph doesn't do is it does everything in steps of 1, whereas what we're missing out on is these tiny little changes. As A gets closer and closer to 0, the graph gets closer and closer to that center point. But as I increase it beyond that, it gets further and further away. So just move the calculator out of the way there for a sec. Alright. So that's your hyperbola. You solve it as you would any other equation. So for example, three 3 equals 2 over x plus 1 minus 2. If I wanted to solve that, I would do it the same way I would solve any other equation. I would take the minus 2, move it over to the side. So I would add 2 to both sides. I would now have 5 equals 2 over x plus 1. Now I would move the entirety of the denominator of that fraction. So it's not just the plus 1, it's everything. This 2 is being divided by x plus 1, not x, not plus 1, x plus 1. So if I multiply both sides by x plus 1, I end up with this situation here. Like so. Now, I have an x plus 1 object on the bottom of this fraction, and then I have an x plus 1 on top of the fraction, which therefore means that I can cancel those out. This is the only time when I can cancel these out. So I'm going to draw a nice rainbow pen and go right through those to get rid of them. Look at that, it's all sparkly. Ooh, shiny. Alright, and then I am left with the equation 5x plus 1 equals 2, which then I can very easily solve, expand. 5x plus 5 equals 2, x equals minus 3 over 5. So obviously I minus 5 from both sides to get minus 3 and then divide by the 5. Alright. Again, this will go up on YouTube if we need it. Alright. So this can also be used to find intercepts. Remember, if the graph hasn't been translated left or right, up or down, there aren't going to be any intercepts because remember the asymptotes are on the axes. So what we need to do then is, so we would then go back and solve them in a way. So for example, 0 equals 1 over x plus 2 minus 3. What are our intercepts for this graph going to be? So y equals, what are our intercepts going to be? Remember that when x equals 0, we can get our y-intercept. Yep. Are you sure about that, Hawa? Alright, because remember when x equals 0, let's get rid of these little dots here. Yeah, oh wait. Alright, when x equals 0, y equals, so y is going to be equal to 1 over 0 plus 2 minus 3. So y is going to be equal to 1 over 2 minus 3, which is therefore going to be y equals negative 2.5. Alright. Now, on the other hand, if y equals 0, we can get our x-intercept. So 0 equals 1 over x plus 2 minus 3. Add 3 to both sides. We get 3 equals 1 over x plus 2. Which means that we can then multiply both sides by x plus 2. We get that. 3x plus 6 equals 1. Again, and then solve. So subtract 6 from both sides. 3x equals minus 5. And then I'm just going to move my whiteboard around a little bit, just so I have a bit of room to work with. And what do I get? X equals minus 5 over 3. So my intercepts are going to be at negative 2, so 0, negative 2.5. And the y-intercept is going to be at negative 5 over 3. Alright, so we can check our answer with our CAS calculator. The negative answer doesn't tell us anything specific about the graph, it just tells us where our intercepts are going to be. So for example, we need to set our sliders so that we have what matches. So obviously if it's a over x minus h, and so therefore we need h to be minus 2, because minus 2 is plus 2 as it is up on the graph, and then minus 3 down there. So again, using our CAS analysis, G-solve, root will get us our x-intercept at negative 1.666667, which is negative 5 over 3. And then we have our G-solve y-intercept. That tells us at x equals 0, y equals minus 2.5. So the calculations that I did are correct. Alright, I'm just going to quickly do a second roll check just to make sure I've got everyone's here. Yeah, Sally's here, BAT, Nita's here. Mr. Oyasi's here. Sadar's here. cells here. So missing Zyguna said, oh yeah, Critty's here. Alright. Alright. So in terms of hyperbolas, that's all we really need for now. So now we're going to move on and do the truncus work. So a truncus looks like a tree trunk, hence the name. I don't know whether I don't know which one came first, one or the other, but we have what we have. All right, so I'm now going to erase what I've got here. Again, the video will go up later. Now, truncuses are very similar to hyperbola, which is why they're lumped in together. And what we have is y equals a x minus h squared plus k. All right, very similar to, very similar to hyperbola, except it's got this, the whole bottom, the denominator of the fraction, is in brackets and it is squared. And what that does is it creates a lovely little situation where the graph, I'm just going to, you really need to just use the ruler. That's what it's there for. Problem is it keeps coming on a 45-degree angle. It's very irritating. And a graph of a truncus of this form, so we'll assume h is 0, so this is going to be y equals 1 on x squared. And the graph will look something what have I done there? Pen's gone a little crazy. Graph will look something like this, like a tree trunk. Obviously, it's supposed to be symmetrical, it's supposed to be nice and neat. Try drawing that again. All right, and it still has the same asymptotes as before. Down the middle, and across the bottom here. The only difference is that a truncus never exists in this bottom half of the graph. All right, never ever exists down the bottom. And we can see that if we go over to our CAS. I'm now going to change my graph to a truncus, and I'm going to move, so go back to 0 and 0. And now what my graph does is it starts in the bottom here, goes all the way up, hits the other asymptote, comes all the way back down. I say hit, never hits. It gets infinitely close, but it never ever touches that asymptote. All right, and I can move these graphs around the same way I would normally. The only difference is that the graph looks like this. Now, what you'll notice is that it gets much, much closer to the graph than the hyperbola does. So 1 over x. For comparison, as you can see, it gets much, much closer to the asymptote than what's going on here. Yes. So if you were thinking about this graph in terms of domain and range, the range would be from 0, but not including 0, all the way up to positive infinity. It would never ever have a negative y value. All right. So we'll talk about domain and range next week sometime. So if you go to the table function and we set up our table, we're going to set up our table, start at -5, go to 5, and we're going to go in 0.25 steps. All right. And as you can see, for our graph, let's just turn that off for a sec. As you can see, it has that error at the asymptote still. The error just simply means that's where the asymptote is, because you cannot divide by 0. Because therefore it would be a divided by 0, which can't be done. And as you can see there, the numbers get really big there with 16, for example. As we get closer, that would be, if I want to make that table even more granular, we'll do 0.1 steps. It starts off really small, because you're thinking, well, that's a over -5 squared minus 5 squared is 25. So it's 1 over 25 plus 0. 1 over 25 happens to be 0.04. As we get closer and closer, see here, the graph quickly accelerates, because remember, a negative number squared is still a positive number. That's why the graph doesn't exist in the negative. All right, I'm just gonna bring this over briefly. So this is part of the table of values I really care about, because I can see as my values get closer and closer to where the asymptote is, they accelerate up very quickly. They hit the asymptote, and then they start going back down very quickly. All right, you would solve this the same way you would anything else. So let's go back and we'll try and solve an equation like this. So if I have moved my truncus around, if I, for example, have moved the bottom asymptote down, does anyone want to take a guess at how many intercepts I'm going to start having? I've moved the graph down and to the left. How many intercepts do I now have? How many intercepts? Not necessarily X or Y. How many intercepts in total am I now going to have? It's definitely more than just 1. Two. I'm going to have 2 of something, but the answer is going to be more than 2. I've moved it down and to the left. All right? So if I move it down, I have changed my k value. And if I've moved it to the left, how many intercepts does that graph have? It now has 3. All right, so I have a y-intercept here, just the one, but I now have 2 x-intercepts. I now have 2 x-intercepts. All right, so this here is 1 over x plus 2 all squared minus 3. So let's actually do this one. So y equals 1 over x plus 2 squared minus 3. Alright, if I want my x-intercept, I remember I have to make y equals 0. So 0 equals 1 over x plus 2 squared minus 3. Add 3 to both sides. 3 equals 1 over x plus 2 squared. I now take my denominator and put it up the top. 3 equals x plus 2, no, not 3 equals, 3 times x plus 2 squared equals 1. Now, problem is, where do I go from here? What am I going to do next? Because the question is it worth me doing any sort of expansion nonsense with this? Is it worth... Okay, take the square root on both sides. There's a problem with that, in that I cannot do the square root yet. I have to move the 3 first. So if I move the 3 first, I end up with x plus 2 squared equals 1 over 3. So here, I can now start doing things. Now remember, if I take the square root of both sides, what am I going to then create? What am I going to then create on both sides? What am I going to then create on both sides? What happens when I take the square root of something? I don't just have one answer, do I? I have what? If I take the square root of... So if I take the square root of 9, what's my answer? It's plus and minus 3. Alright, I take the square root of anything, I have the plus and the minus of that. So, in the case of my equation here, just going to move this this out of the way a little bit. Yep, put it about there, I think. I'll eventually get better at doing this. So I take the square root of both sides, and then what that's going to do is I'm going to be left with x plus 2 on the left-hand side, and I'm going to have plus minus the square root of 1 over 3. And then I would then solve from there by subtracting 2 from both sides. So my intercepts are going to be at x equals minus 2 plus minus the square root of a third. Now, if you guys remember back to your thirds thing I asked you to the square root things I asked you to do at the end of last term, that 1/3 square rooted can be simplified. Alright, if you remember, the square root of 1 over 3 is equal to the square root of 1 over the square root of 3, which means it's 1 on root 3, multiply both sides by root 3 over 3, and I end up with root 3 over 3 plus minus because of what we're dealing with here. So my answer's going to be x equals minus 2 plus minus 3 on 3. Alright, it's very improper to leave a fraction inside a square root symbol. It is also very, very messy to leave a square root on the denominator of a fraction. Alright, so we want to rationalize the denominator. We get something nice and clean like this. And if we check our answers on our CAS GSolve, we have root negative 2.57735 and negative 1.42265. Alright, so if we go back to our CAS and we go to the main menu and we ask it, okay, solve y equals 1 on, solve equals 0 equals 1 on x plus 2 squared minus 3 comma x, and it gives me negative 2 plus minus 3 root 3, root 3 over 3. See? That's how I know my answers are correct. Alright. Luckily, the y-intercept is much easier to do. It doesn't require any of this sort of shenanigans. So what we'll do is, I'll just move that over here. Let's make a new one. Y equals 1 on minus 3. To find the y-intercept, I make x equals 0, y equals 1 on 0 plus 2 squared minus 3. So that's y equals 1 on 4. Minus 3, y equals negative 2 and 3/4. So y should be equal to negative 2.75. And we'll go back to our graph because it hasn't gone anywhere. We go analysis, G-solve, y-intercept, and there it is. Y equals negative 2.75. All right. Thank you for bearing with me while I record this. It's gone on a little bit longer than I thought it would. So what I'm going to ask you to do today, before the next class, hopefully, is to complete 4A and 4B, which is about these two things. Most of you should have already done 4A. So 4B is the new stuff regarding the truncuses. And hopefully what you'll be able to do is take a photo of your workbook, of the things that you've done today, and send it to me through my emails. All right, make sure that you have labeled it properly. All right, so I'm going to stop the recording here, and you guys can go off and do whatever it is you need to do.